Alex Wade from UCL will present about the portability and scalability of MD code. So, Alex, 15 minutes.
Thanks. Morning, everyone. I'm Alex, and I'm going to talk about some of the work we've been doing in Peter's group on binding affinity calculations, specifically talking about the scalability of these calculations to large resources and some of the strategies we have for the portability of these methods, and then maybe some of the future ideas that we could implement with new standards like OneAPI and things like this. Before I get into any specifics, I will just give some high-level overview of what a binding free energy is and why we're interested in calculating it. So in drug design, we might be interested in finding a small molecule which binds non-covalently to a protein, and this protein would be involved in the mechanism of action of some disease, and then by binding to it, we can inhibit its action. So an oversimplification is that this binding affinity is then a proxy for the effectiveness of the drug. So these binding affinities is what TIES calculates, but how do we perform this calculation? So TIES is an alchemical method, and in the computer we can perform alchemy. So we change one set of atoms into another, say maybe A to B, and over the course of this transformation we run molecular dynamic simulations. And the analysis of these simulations can tell us which set of atoms were preferred. So in terms of a favorable binding affinity. So the important thing to understand for the scalability of these calculations is that as we transform from atoms A to B, we do this in discrete steps, and then we call these steps lambda windows. Within each lambda window, we're running repeats of these molecular dynamic simulations, and it's important to run these repeats because the molecular dynamic simulations are going to return a distribution of results. So if we want accurate and precise results, we need to be running replicas. And then the general idea is that these lambda windows and repeat simulations are all independent. And so here already we have two domains over which we can achieve some parallelism. Typically for these calculations, we might have, say, 13 lambda windows and 5 repeat calculations. So just for one binding affinity calculation, this is already 65 maybe nodes or GPUs that we'd be using. So this idea of running the repeats in each alchemical window is kind of what makes TIES unique in the literature. It's not a method I've come up with, it's something that Peter's group have been working on for a long time. Many iterations of this software now. The most recent iteration was done by a previous group member, Matt, and he created TIES 20, and this forms the automatic setup for the protein and the ligands which are used as input to these kind of simulations. So this is what it would look like diagrammatically, where we have TIES 20, which builds the input, and then this is farmed out to the alchemical windows and the replica simulations, which are all in parallel. And then you have some sequential steps, which are for MD type things, equilibration and production simulations and analysis. But since these are sequential, we can't achieve any parallelism there. In terms of portability, our method currently is that since our calculations rely on these molecular dynamics engines, we can exploit the fact that some of them are better designed for CPU or GPU, and essentially because TIES is a wrapper around these molecular dynamics programs, we can switch between the two different programs at will. And typically we might use NAMD on a big multi-node CPU machine, but OpenMM on GPU machines with accelerators. But the kind of central idea here is that there's some embarrassingly parallel nature to these calculations, but there are other areas in which we can achieve parallelism to use larger resources. So this is one example of this, where we might be doing some kind of parametric uncertainty quantification, and the results I'm showing here are for a reproducibility study, where we're looking at reproducibility across the two molecular dynamics engines we commonly use, NAMD and OpenMM, but also reproducibility across some analysis methods which are commonly used. So you can imagine here that we have these 65 simulations for each binding affinity calculation, but then we have repeats for the different engines, the different analysis methods, and you can go deeper on this as well. And other members of Peter's group have done more in-depth uncertainty quantification on NAMD, for instance, looking at 127 free parameters which are input to the engine and quantifying uncertainty on this. So the results I show here are just for one protein system with 10 or so ligands, but the whole of the study was 5 protein systems with 55 ligands. So we also get some parallelism there across the ligands, and the general results are, as long as we're running these replica simulations and quantifying the uncertainty, we can get good agreement between the molecular dynamics engines, and we always see very good agreement between the analysis methods. This then is kind of parametric uncertainty quantification, but we can also do an aleatoric uncertainty quantification on these types of calculations. And I already spoke about how, as we run these molecular dynamics simulations, we get a distribution of answers. So here I'm showing the results where we've run large replicas of simulations, so up to 320 here, where typically we might use 5. That's figure A, and then figures B, C, and D are subsets of 32 replicas for these simulations. And the general idea here is that even at the level of 32 replicas, we're still seeing some variance in these distributions. And 32 replicas is 10 times what might typically be used in the literature. So it kind of highlights the importance of these replica simulations. Since we've got so many replicas now, up to 320, it's very easy to use a lot of resources, and the example I've given here is Archer 2, which is where these simulations were run. We ran the simulations in batches of 135, and then this immediately allows us to use almost 1,800 nodes on Archer just in one submission. The final area in which we can achieve some parallelism is what I've called here kind of methodological. So in a drug design campaign, we're looking for maybe one drug or a family of drugs which bind well to the protein, but we have to sort through many other drugs which do not bind well or not at all, or have some other undesirable properties to them. And this, we could be searching through hundreds, thousands, hundreds of thousands. We heard from Austin Clyde yesterday, his screening work, and this is almost 12 million compounds, I think he's looking through that. So there's a lot to search through. A good example of this is fluorine scanning. So this is a methodology where we might take a drug which is close to being at the end of the pipeline of drug discovery or already developed, and then you would systematically swap out every hydrogen or combinations of hydrogens for fluorine. And so you can very quickly generate large numbers of candidate drugs which you might want to test to see if they improve the binding affinity at all. And the example I give here is something we're running on Summit currently, where if we were just looking at, say, 24 fluorinations or fluorinated analog compounds, we're then already using almost 1,600 GPUs on a machine like Summit. To set up these kind of calculations, we've developed TIES software, and we're currently in the process of making a new release for this software. So not only does this set up the input, but it also sets up and orchestrates these alchemical windows and replica simulations. And part of the newest release, we have an API now for these TIES programs. This is an example of what I'm showing here. So in lines 1 to 11, we're performing the work of TIES 20, setting up the inputs. And then 12 to 13, we run the simulation. 14 to 15, this is doing the analysis. And then you can imagine an external loop around all of this, which would be looping over all of the compounds that you're interested in, or all of the parameters you want to run uncertainty quantification on. So I spoke a little bit about the strategy that we have for portability, which is switching between these codes. And this gives us portability across CPU machines, GPU, AMD, and NVIDIA. But we've heard today and yesterday about these new Intel GPUs and how these are going to feature heavily in upcoming machines like Aurora. So we want to make sure that our methodologies are robust for these new platforms. So part of this new hardware release that Intel is making, they're also bringing out tools, and they've termed these tools and methods kind of a OneAPI. The goal of this is partly to unify programming between GPU and CPU. So on the GPU side of things, they're using a non-proprietary existing standard, which is called SQL 2020. So the question is then, if we want to be as ready as possible to run on these Intel machines when we get access to them, can we take a molecular dynamics code like OpenMM and run this with SQL? So this is what I'm showing here, where OpenMM has CUDA code in it. So can we take this, a small portion of this CUDA code, and run it through Intel's compatibility tools, which they say can convert 95% of CUDA into SQL. So for this small case here, where we've taken just the bonded kernel, which is the part of the code which is responsible for calculating the bonded forces of the system, and we run this through the compatibility tool, then okay, this works fine. Then we get the results and we see similar performance, but there's no optimization on this code, and the cards I'm considering here are not exactly equivalent, but it proves the point that the compatibility tool works. So then can we just take all of the other kernels in OpenMM and run these through the compatibility tool to convert the whole code? Well, no. So what I showed in the previous slide is a simplification. So we've skipped a crucial part of OpenMM, which is runtime compilation. So to achieve their existing level of portability between AMD and NVIDIA cards, OpenMM uses a strategy of runtime compilation, essentially building the kernel at runtime for the specific platform they want to run on. And this is not supported by the compatibility tool. I don't know why this is left out. I know of other codes which also use this strategy for portability. But yeah, it's a shame that it's missing, and it means that it would take significantly more effort for us to make this kind of port. Everything would have to be done by hand. The compatibility tool is not so useful here. So does this mean that we can't run on these Intel machines? Well, as far as we understand currently, it should still be possible to use OpenMM via OpenCL on these upcoming Intel cards, but in terms of how feasible this is or the performance, we still need to get hold of a testbed for this. And we're in the process of applying to machines like Articus, which say that they have these Intel GPUs on. So this is ongoing work still. So yeah, with that, I conclude and give my thanks to our sponsors and collaborators, specifically the people in Preet's group working on these binding for energy calculations, Shanzu and Agastia and Matt. Thank you for listening.
Thanks, Alex.